So today we're going to be looking at the symbol pi. So this little bad boy in my heading here, this is a symbol that was used by the ancient Greeks to basically give us a ratio between two important points of our circle. So this symbol of pi relates our circumference, so our entire border of our circle, and it relates this to the diameter. Sorry, I've drawn that a bit badly. Let's try that again. Good enough. Now, this is basically a ratio between our circumference and our diameter. Now, this symbol is an irrational number. So it has a bunch of digits. Computers have given an exact value to this. Well, not an exact value, but values to a number of different decimal points. But in this video, we are just going to look at just giving you a bit of a background into the term pi and how we can use this to come up with a formula for finding our circumference using the diameter and the estimation for pi we come up with here. Now, I'm going to give you a very brief look into estimating pi, as well as giving you a background as to how Archimedes, the ancient Greek mathematician, was able to come up with a more accurate value for this ratio here. So taking a circle, let's draw one here. We are basically going to look at two cases. A case in which we are going to take two types of borders around our circle. Now, circles were very problematic for ancient Greek mathematicians because they were used to dealing with straight lines, squares, rectangles, a bunch of other shapes, but circles were all around them, but they couldn't find a way to deal with these because of the curves. The curved edges made these very problematic. So what Archimedes did was he tried to look at the circle in terms of shapes he knew. So a very common one he did was through hexagons, which we'll get to in a minute. But for 1 minute, we're going to consider this circle here with a radius of 1. And we are going to come up with an estimation for pi. Now, say I draw a rectangular border around my circle. Just pretend those are straight lines. I know it's a bit of a dodgy drawing, but bear with me. Now, what would be the dimensions of this square here? Well, the radius is 1, so I'm going to just extend this toward the diameter, which will give me a diameter of 2 altogether from this point to this point. Now that means from one edge to the other edge of my square is going to be 2 units long. So that's going to be 2 units here. Now, the radius of a circle just spans from its center out to any of the borders. So we can also say that, we can also say that this distance here is 1 unit as well, because that's a radius, as well as this distance. So from this top edge to this bottom edge, we also get 2 units. Now, we can clearly see that if we're looking at perimeters and borders here, if I were to approximate the circle the length of the border of this circle in comparison to the square that encloses it, well, the square is going to be, it's going to have a larger perimeter than the circle. So we can say that the circumference is going to be, well, actually, sorry. We said that pi was, it's a ratio between circumference and diameter. So we can say here that our pi is going to be smaller than my than my perimeter of the square here. So it's going to be smaller than 8 over 2 because my diameter is 2 and my circumference, well, the border of my square is 8. But we are just treating this as an upper bound, sort of like a maximum value for the circumference of our circle. So we can say that pi is going to be smaller than 4. Because there's no way that this is going to be a greater perimeter than the outside square. So we can say pi is less than 4. Now, taking another circle, we're going to observe something else that happens. Here we go, it's better. So, we're going to now look at a hexagon. Now, what I'm going to do is I'm going to enclose this hexagon. Well, it's going to be within my circle as opposed to the square outside it. And now, once again, this is a circle of radius 1. Now, I want to find what perimeter my hexagon is. And I know that my circumference is going to be greater than this because you can see we're sort of like taking shortcuts here. Instead of going all the way around the curve, I'm cutting across here. I'm doing an edge inside. And I'm essentially cutting my circumference short. So this estimate we come up with is going to be, pi is going to be greater than that. Now, well, it's a little bit tricky here, right? We don't exactly know what these lengths are. We have a radius of 1, and we know that all the way through to here will be 2 units, but we don't know what each of these sides are because these don't represent our radius. These are pretty much segments in our circle cut out. But let's just do something here. If I were to construct, well, if I were to just break this hexagon up into 6 little triangles, my entire angle sum here has to be 360 degrees. So each of these angles are equally going to, they're all going to be equal and they're all going to add up to 360. Now there's 6 lots of this angle here. So taking 360 divided by 6, we get that this is an angle of 60 degrees. Now, an important thing to note, each of these sides are equal. Now, why are they equal? Because each side is the radius. We're stretching from the center of the circle out to the outside border. So each of these are going to be equal. So I can write, I'll just finish writing in all my angles here. 60 degrees, 60 degrees, 60 degrees, and 60 degrees. And all of these sides, 1, 2, 3, 4, 5, 6, are going to have a radius of 1 based on the unit we talked about earlier. Now, if these two sides are equal, let's take this triangle down here. These two sides are equal, and as a result, these two angles are going to be equal. Because as a property of triangles, which we talked about previously in angle geometry and shape geometry, that equal sides mean that the angles opposing these sides are equal. Now, I have 60 degrees here. So that means that these two angles, they have to sum up to give us 120 degrees because our angle sum of a triangle is 180 degrees. Now 60 has been taken up here. So that means I have two equal sides divvied up, which pretty much make up 120. So what's 120 divided by 2? Well, that is 60 as well. So we can say that these are all equilateral triangles. So that means that I'm going to have a length of 1 here, a length of 1 here, and a length of 1 here. And that goes for all of these sides. Now, the ones we're interested in are the border sides here. Each, which we know now, are of a length of 1 unit. So adding all these up, 1, 2, 3, 4, 5, 6, our estimate for pi has to be greater than 6 over 2. Using the same thing we did here, relating our circumference and diameter, the ratio of the circumference to the diameter in this example has to be greater than 3. So we don't know anything about pi yet, but we know that it has to sit between 3 and 4. Now, obviously you'll see in your textbooks, pi approximates out to be about roughly 3.14 and so on and so forth. So to give you the kind of abridged short version of this, what Archimedes did was he looked at this idea of upper bounds and lower bounds within our circle. So he did this using hexagons to start off with. So he did an outside hexagon, an outer hexagon, I should say, and here, 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 and here. Sorry for the bad drawing, but hopefully you get the idea. He had an inside one as well. And he said that, well, this circumference and my estimate for pi should sit somewhere between my lower bound, my lower approximation, and my higher approximation. So he got a better estimate when he looked at 6-sided shapes. And then what he noticed was, well, as we just add more shapes to our polygon, let's look at what happens. So if we, for example, looked at a 12-sided polygon. Now, this isn't going to be drawn very well, but let's say we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, the extra sides mean that it starts to look a little more circular. Now, let's say I took 24 sides. Well, drawing this badly again, but hopefully you'll get the idea. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. It's looking a little bit more circular. And we notice that the more sides we add, the more our polygon, starting off as a hexagon, the more that begins to look like a circle. Now, people often say that circles essentially have an infinite number of sides, that the more sides we have, as we increase our sides of our polygon to infinity, we get a shape that looks closer and closer and closer to a circle. Now, what Archimedes did is he did some very advanced trigonometry that we're not even going to get into here, but he essentially worked all the way up to a 96-sided polygon. So he took a polygon with 96 sides, and he meticulously chipped away at this to get a more accurate approximation for pi. And he basically called it at 96 sides. But this is where we get our textbook definition for pi. So you'll see in your textbooks that often you get that pi equals 3.1415, I think it is, and then so on and so forth. But the process for actually getting this was this idea here. The idea of saying, well, pi relates my circumference to my diameter. It's essentially the ratio of circumference and diameter, as we showed up here. So to get an approximation for what pi is, we're looking at a value it could be higher than, as well as a value that it can be lower than. And by adding more sides, we are gradually closing these bounds, smaller and smaller and smaller. So here we had a pretty large kind of discrepancy here. This doesn't tell us much that pi is between 3 and 4, but by adding more polygons, we slowly close these. We bring these numbers, these two bounds, closer and closer together, and this gives us a more accurate approximation for pi. Now that we know that this sort of value for pi, to find the circumference of our circle, C, we just get that by multiplying pi, this irrational value that we found, and multiplying that by the diameter. And we could have also gotten this from just rearranging our equation. If pi equals the circumference divided by the diameter, because this is a ratio, then we can express the circumference as a product of pi and the diameter. But this is a little bit of a longer, drawn-out introduction into how pi was created, because it's quite significant and it often gets glossed over a little bit. We just jump straight into this. We give you this in textbooks and you just start to work with it. And that's great, but hopefully this video gave you a little bit more of an insight into how pi came to be and some of the really fantastic work that Archimedes did to come up with this approximation, and as well as a lot of other important ideas and formulas around our circle, which is naturally very hard to deal with because of these curved edges. Now, in the next video, we're going to look at just some examples of applying the formula we have just derived. And then in future videos, we're going to look at not only the perimeter or the circumference of the circle, but also the area of the circle. So I'll see you there.